So, first of all, I would like to thank the organizers for this opportunity. It's a wonderful place. I'm really happy to be here. So, as you can see, this talk is about the correspondence between infinite dimensional Poisson-Lie groups and Lie bialgebras. Okay. So the goal of this talk is to first we will define Poisson structures on infinite dimensional manifolds and Lie groups, which are modeled on a convenient topological vector space. So these are locally convex topological vector spaces which are Mackey complete, and the other way to characterize them is like all the curves on that space is Riemann integrable, 0 to 1. Okay. Then we will define Lie bialgebra structures on convenient Lie algebras. So by convenient Lie algebra, I mean that this Lie algebra are also modeled on a convenient topological vector space, and the morphism, the Lie bracket, is conveniently smooth, means is just bounded. Okay, and then we will show that from a Poisson structure on a convenient Lie group, we will construct a Lie bialgebra structures on its Lie algebra G. Of course, I will define both of it. So this direction works in much more generality. But for the converse part, we have to assume that a Lie group is modeled on a nuclear Fréchet or nuclear Silva space, which are just a particular case of convenient topological vector space. If you don't remember the definition, so this nuclear Fréchet and nuclear Silva spaces are just the projective and direct limit of Hilbert spaces, which with the linking maps are trace class operators. Okay, and then we have to assume that our G is connected, simply connected, and it's regularly grouped in the sense of Milnor and also Kriegel and Mikol in the convenient setting, which means all the smooth curves on the Lie algebra can be smoothly integrated to the Lie group. Okay, so if this is the case, then we can actually show that all the continuous Poisson bracket on C infinity G and the Poisson tensors on G and the Lie continuous Lie bialgebra structure on the Lie algebra G, these are in one-to-one correspondence. But why this is the nice enough class of Poisson-Lie group? Because we have important examples that are inside there. So like this smooth loop groups and diffeomorphism group of circles, these are nuclear Fréchet groups, and this analytic loop group is a nuclear Silva topological space. Okay, so this is indeed a nice class. Okay, so first of all, why are we modeling our Lie group on nuclear Fréchet and nuclear Silva spaces? So if you remember from the last talk of Barbara, yesterday's talk, there are some problems in the infinite dimensional setting. So one of the problem was we cannot identify a cotangent space at any point with the differential of all the smooth functions on the manifold. Okay, so but the nuclearity implies the existence of a smooth worm function, and then we can in fact identify this too. And this identification is important because it allows us to get one-to-one correspondence between the Poisson bracket and Poisson tensor. And the second problem was the non-existence of Hamiltonian vector fields. So, and the problem was not all the derivations can be given in terms of the smooth vector fields on the manifold. But if your manifold is modeled on a nuclear Fréchet or nuclear Silva space, in fact, we have a topological isomorphism between all the continuous derivations on C infinity M and all smooth vector fields on M. Then we can, so that would mean that we will always have, for given a Poisson bracket, we will always have a existence of a smooth vector field, the Hamiltonian vector fields. So this solves the problem that we had in the infinite dimensional setting. So let me directly go to the definition of infinite dimensional Poisson structure on a manifold M, which is modeled on a infinite dimensional convenient topological vector space. So we will say that this pair M with a vector bundle F and this rho is a Poisson structure on M if this F is a vector bundle over M, convenient vector bundle over M, which is a subset of this convenient vector bundle, this cotangent bundle of the manifold. It has a convenient manifold structure. I see. Yeah. So this T star, this T prime M, this is a convenient manifold. It has a convenient manifold structure. This is just the space of all conveniently smooth covectors at every point. Okay. So this F is just the subspace, and what we need that the canonical injection between from this F to T prime M. So we need that this map should be conveniently smooth. So at every fiber this should be a bounded map. And then what else we need? We need that this F is in duality with Tm, which means at every point this Fx separates point of this tangent space Txm. Okay, and what? So and then we need this anchor map rho from F to M. So this map should define a Lie bracket on the sections of this vector bundle F, like this. So this this Lie bracket is defined as follows. So you pair this beta with rho alpha, which is then you will get a smooth function, and then you take the derivative of this conveniently smooth function, and then you take the derivative at this point P. This should define a Lie bracket on the sections of F. Then we will say that this pair F, M, F, and rho is a Poisson structure on M. And then we can define a Poisson bivector just by pairing beta with rho alpha. So by the way, why do we need this this separability condition that this Fx separates point on Tm? Because so first of all, the image of this rho is inside Tm. So this means for any alpha in the sections of this vector bundle, this rho alpha will define a vector field, Hamiltonian vector field, and we need this separability condition to show that is a unique, that Hamiltonian vector field is unique. Okay.
Do you mean point separating?
Yes. At every point, this Fx should separate point of Tx. Okay, so now we will go to the definition of Poisson-Lie group. So this Poisson-Lie group is a Lie group G with a convenient Poisson structure. But I wrote, so this is a pair G, F, FB, and rho. So I wrote FB because this vector bundle FB is given by, is just a trivial vector bundle given by some convenient subspace of G prime. Okay. And then what we need that this Poisson structure should be compatible with respect to the group structure of G, which means that the pi we define, the bivector, this should be multiplicative. Then now we go on to define the conveniently bialgebra structure. So this is again a pair of G, B, and this delta. So this G is a Lie algebra, and this B is a subset of this dual, bounded dual. Okay. So this is a and what we need a map delta from G to the space of all alternating bilinear maps on B. So this map will be well defined. To make it well defined, we have to assume that the smooth coadjoint action of G on G star restrict to the convenient smooth action of G on B. Okay. Then we assume that this delta is one cocycle of this Lie algebra G, as in the case of finite dimensional case. And then what we need that if you restrict the dual of this map on B times B, then it should define a Lie bracket on B. Okay. So then we will say this collection Lie bialgebra structure on G. Okay. So now so now we will construct a Lie bialgebra structure from the Poisson-Lie group structure on G. Okay. So how do we go to prove this? So from pi we can write translate it. We can write translate it to get this map theta. This theta is a map from G to the all the bilinear map, alternative bilinear maps on B. So we can show that because pi is multiplicative, this map theta will be a smooth one cocycle of G. Okay. And but there is another way to see this. This is like if you define this map delta tilde by like this. So first component is just x, and second component is this theta. So then this will be a Lie group homomorphism. This one cocycle is same as this map being a Lie group homomorphism. And then we can just differentiate this map to get a Lie algebra homomorphism. Let's say this is the delta tilde, and this is same as the second component being a smooth one cocycle of the Lie algebra G. This is one of the conditions that we wanted for the to define a Lie bialgebra structure. And what else we need? We need to show that the dual of this map defines a Lie bracket on B. Okay. So, but this is again so what we can show that this delta. So if you pick alpha beta in B, then this delta of alpha beta is same as the differential of this function. Sorry, this should be delta tilde, sorry, beta tilde and alpha tilde. So this alpha tilde and beta tilde are the one forms defined by the but just by the right translation of this element alpha and beta of B. So if you pair this with beta with rho alpha, you will get a convenient smooth function, and then you take the derivative of this function at identity. So, but we already know that this will define a this will define a Lie bracket on the sections of F. So this will give a Lie bracket on B as well. So we have this convenient smooth Lie bracket on B. So by the way, convenient smooth Lie bracket means this Lie bracket is just bounded map. But if you assume that B is Fréchet or Silva, you can show that this map is also continuous. So you will get a continuous Lie bialgebra structure on G. Okay. I mean, yeah. So now we go to okay. So that was the one direction. So we started with a Poisson-Lie group structure, and then we constructed a convenient smoothly bialgebra structure on G. And if the modeling space is Fréchet nuclear or Fréchet Silva, then in fact we got the continuously bialgebra structure. So now for the converse part, we have to assume that our Lie algebra G is modeled on a nuclear Fréchet or nuclear Silva topological vector space, and we have to assume that this G is smoothly regular, simply connected Lie group of the G. Then we can show that the Lie bialgebra structure on G given by the G delta and G and its dual. This is a continuous dual. It's the same as bounded dual because this Fréchet nuclear and Fréchet Silva are these are Montel, so it's the same. Okay, so we will show that this will give us a Poisson structure on G with this vector bundle. Okay. So for this, we will need Lie's second fundamental theorem, which says that so if you take any Lie algebra G and H, infinite dimensional, and if you assume that this H is regular, H is regular and G is connected, so the Lie group corresponding to this Lie algebra H is regular, and if the Lie group corresponding to this Lie algebra G is simply connected, then you can integrate any continuous Lie algebra homomorphism to get a smooth Lie group homomorphism, or a bounded Lie group Lie algebra homomorphism to get a convenient smooth Lie group homomorphism. Okay. So we will use this theorem. For this for our delta, which was the one cocycle. So what was it? Yeah. So we had this map delta. So it is same as this Lie algebra homomorphism. So because we assume that the Lie group corresponding to this Lie algebra G is regular, so if you take the semi-direct product of G with L2B, it will again be regular, and the Lie group corresponding to this G is anyway simply connected. So you can integrate this Lie algebra homomorphism to get this theta. Okay. And yeah, so theta, which will be a smooth one cocycle, but this is same as this pi being multiplicative. So starting from a one cocycle on the Lie algebra level, we got the multiplicative bivector field on G. But story is not done yet, because we have to show that this pi is in fact Poisson. Like we have to show that it actually so it implies Jacobi identity. Then we can conclude that this our G with this pi is actually a Poisson Lie group. Okay, and for that, what we will do, so first we, so okay, so forget about this, but yeah, so what we can show that if the modeling space is Fréchet nuclear or Silva nuclear, then the sections of this vector bundle, like the vector bundle where each fiber is alternating k-linear maps from the cotangent space at that point. Section of this is actually topologically isomorphic to the sections of wedge product of TG. This wedge product is just the schizometric part of the projective tensor products. Okay, so we can, so if G is nuclear Fréchet or nuclear Silva, we have this topological isomorphism, and then on this kind of object, we can define the Southern bracket like this. So this will be just the unique extension of this map, which is same as the case of finite dimensional case. Okay, so this has all the usual properties of the Southern bracket, like graded schizometricity, graded Leibniz, and graded Jacobi identity. And using this property, we can show that if pi is multiplicative, then Southern bracket itself is again multiplicative. And then we can play the same game. We can again right translate it to get a one cycle, which is same as this Lie group homomorphism, and that, and so we can, and if you differentiate it, one of the component will be one cycle of the Lie algebra G. But this bracket of this delta with itself, what this is actually same as the dual of this Jacobian of the Lie algebra on G star, which is 0, because we have this Lie algebra on the G star. Okay, so what we have, that this delta with this bracket of delta with itself is 0. So that, but we have one-to-one correspondence between all the one cycles on the Lie algebra and one cycles on the Lie group. So this is 0. That means that this delta, this theta with its this bracket has to be 0. So this multiplicative bivector has to be 0. So this the Southern bracket of pi with itself is 0. This is another criteria of this pi being Poisson. This means that this pi actually satisfies the Jacobi identity, and then we are done. I think, yeah. Thank you.